This is a short video about the assumptions behind regression analysis, and the important takeaway has to do with the value of looking at residuals and appreciating just how robust linear regression is, not to panic you about the assumptions behind it, which will never be satisfied, but it's not that important that they be satisfied. They're clues to how to do a better analysis when they're violated. So first, what are the assumptions? So I'm just going to show this in 2 dimensions so I can draw pictures, but the same thing holds in multiple dimensions if you have a lot of x variables. Suppose you had 1 x variable and 1 y variable. So there is an assumption that the y value is normally distributed, and it has a mean given by the straight line. So we're assuming is a linear model that y has a linear function with respect to x, has an intercept and a constant slope, and a standard deviation that is actually constant. We'll get to that assumption in a second. So it's the assumption that y is normally distributed around this mean, this average line. So normal distribution. When you have very skewed distributions, that means that possibly using a logarithm of y would make more sense than using y itself, because one of the assumptions is that it's normally distributed. And you'll find with skewed distributions that often the logarithm fits better than the untransformed variable. What we do is we partition the deviation of the points in the line into 2 parts, so that here are some points. You put in the regression line. There's the average value of y. So when you look at the points, they differ from the green line, but they differ for 2 different reasons. The black line tells us we know something about why they deviate from the line, deviate from the average, and that's because according to the black line, there is a relationship with x, and when the value is higher value of x, we'd expect it to be a higher value of y. So you can think of the black line as explaining some of the variation of these points in the line. So we look at the point that's shown right here on the right. That point is higher than the average value of y. We understand the explained part y, because that has to do with it being a relatively high value of x, but we don't understand why it's above the black line. That we call the error variance. It's the unexplained variance. So first, we assume that we have some random sample, which of course we never do. We also assume that it's sufficiently large. There are different rules of thumb about how large a sample has to be. Generally, when you're working with observational data, the good news is that you have plenty of data points, far more than 20, maybe in the order of millions. The bad news is that it's observational data, so it's never a random sample. And even if it's the population data, you're applying it from, let's say, last month to what you think is going to happen next month. It's not a random sample of what's going to happen next month. It's not even a sample of what's going to happen next month. So you're making some grand assumption that it can be treated as a reasonably random sample. Second assumption, the variables are linear related. So that straight line is what you'd expect to find on average, except for random variation. Linear assumption is not that confining though, because you can transform the variables and it can be a linear relationship between the logarithm of x and the logarithm of y, which is a nonlinear relationship of y and x, but it is still linear regression that you can apply. So even a curved relationship, if you have a curved relationship, you could put in a quadratic term, x squared, and it may be y is linear in x and x squared, even though it's not linear in x. We assume y is normally distributed for every value of x in the population. This is called conditional normality. So let's say you had a data that showed how many, it had a measure of prestige of a job y, and that depends or is related to years of education that you have x. And so if you look at a subsample, 12 years of education, high school diploma, you would look at a histogram of the prestige and ask, is it approximately normal? And then you would look at people with 4 years of education, people with a college education, and is it still approximately normal? So we can get a picture of this. Here's some data points. In this case, income versus some measure of happiness. You take a slice around a certain income level, and what you'd want to do is look at a histogram. So turn your head sideways, a histogram of those values within that narrow range of income. Does it look approximately normal? That would be okay. If it looks like the bottom one, it's not okay. Now, the important thing is that not that you violated an assumption here. I think you could still use linear regression, but this is a good clue. When you see residuals, or when you see the values of y that look like this bottom picture, it's a bimodal distribution. You should immediately be thinking, maybe there's two groups in this data. Can I identify what those two groups might be? If it was something like happiness and income, the obvious thing to think about might be gender. Gender is often a variable that identifies two groups quite differently in respect to certain variables. So if it looked like the bottom one, I would be looking that we should be including something like gender or some other grouping. Many demographic variables will identify subgroups. And so instead of looking at a normal distribution, you'd be looking at a bimodal or even a trimodal distribution. This is the hardest assumption to understand, that the variances are relatively constant with respect to X. It has a bad name called homoskedasticity. When it's violated, it's called heteroskedasticity. And what you want to look at is the errors, the unexplained variation at different levels of X. Do they look similar or not? So here's a picture again. Take different slices, different values of X, and look at the errors to see if they are approximately equal. These look pretty good, because if you look within those blue segments, it looks like things are roughly spread out in similar ways. Here's an example that does not look good. As you look in the blue slices, pretty small errors at low values of X. As income goes up, the errors get larger. This is a very common pattern to find, especially when you're looking at monetary magnitudes, prices of homes, income levels. It's pretty common to find that you'll find this cone-shaped pattern. Usually it's errors getting larger as X gets larger. It could be the opposite kind of cone shape, where it's more spread out at low values of X and then gets less spread out as X increases. In either case, it's heteroskedasticity. You have violated a regression assumption. It's not that if you use linear regression and ignore this problem, you've done a horrible thing. Probably, for the most part, it will still work reasonably well. But there is a way to improve upon this. It's called weighted regression. In JUMP, it just means clicking a box for weights and putting in a set of weights. And the whole idea is that what you'd want to do for weighting is, if the pattern looks like this, because of the way least squares regression works, minimizing the sum of the squared deviations of the points from the line, it's going to pay a lot more attention to the segments out on the right than the points on the left. So in order for each of your data points to count equally in your regression model, what you'd want to do is downweight these high error points and increase the weights on the low error points. So it could be something as simple as weighting them by 1 divided by the income. That would put a lower weight on the high incomes and a relatively higher weight on the low incomes. So if you created a new column that said 1 divided by income, and when you do ask for the regression model, there's a box for weight, I'd put that weight in the weight box, and you get weighted regression. And that often will cure this problem. It's not so much that you have to cure the problem as you get better estimates of better model results, better predictions. So in that case, it looks bad. So the conclusion is, First of all, regression is very robust with respect to these assumptions. Even when the assumptions are not satisfied, regression generally works. So it's an extremely reliable technique. You can apply it even when it shouldn't be applied. But the real key is when you find that an assumption is not satisfied, there's usually a next step that it suggests. If the residuals don't look normally distributed, it might be that there's groups in your data. If you have heteroscedasticity, then maybe you should try weighted regression. So there are, it usually suggests things that you can do to improve the model. And there are further diagnostics that you can use, which is looking for outliers, for instance, and usually the best way to diagnose these is by looking at residuals. So let me bring up one more example here. It's a very famous data set called Anscombe's quartet. Anscombe was a French mathematician, and he invented this data set. It's 4 sets of x, y variables. And so if you just draw a graph of y1 and x1, and actually, let me see if I can get them all at the same time. I'm not sure I ever tried this before, so I may get more graphs than I want. I really, let's just see if it works. Y1 by x1. Okay, we don't want y1 by x2. We don't want y1 by x3. Oh, okay, this will work. We want y2 by x2. We want y3 by x3. So I'm just getting rid of the graphs that are not the right sets. And we want y4 by x4. It's a very simple data set, so just looking at it, you can tell that there are these are very different relationships. The top left one looks like a linear relationship with just random scatter. This one looks like a quadratic relationship. This looks like an outlier. It could be an error or some point that's out, but otherwise a perfect straight line. This one looks like really no relationship except for one outlier out here. The reason I asked for all these at the same time is that in JMP, if you hold down the shift key, when you click on this red arrow, and you do fit line. No, I guess it's the control key. Let me remove that. Hold down the control key, and you click on the red arrow and do fit line. It puts it in all the pictures at the same time. Unfortunately, has brought back all those pictures. I guess I need to redo getting rid of these boxes, y1 and x1. Y2 and x2. Y3 and x3. And y4 and x4. And when you look at the regression lines, you'll find that they all look extremely similar. In fact, they're identical. Exactly the same equation will appear. Y is equal to 3 plus 0.5 times x. It has the same r squared. It has the same p-value for x1, same slope of 0.5. So even though the 4 data sets look completely different, the four pictures look the same. Now, because it's such a simple picture, we can obviously see what's wrong looking at these pictures. We have fit a straight line through a quadratic relationship here. We have fit a straight line that's being pulled off by this one point when you really would want to draw a line through the remaining points. And over here, we've drawn a line that doesn't really describe the points at all. It just happens to have one outlier that's putting an upward sloping relationship when there really isn't any. To diagnose this, you really don't need to do more because you can see what's happening. But when you get a bigger data set and more complex data where you have multiple X variables, it's very hard to look at these pictures. It's very hard to find a picture to look at that would tell you if something's gone wrong with the model. So if you hold down Control here and you do, oh, not that one. On this red arrow down here, do plot residuals. I'm not going to bother getting rid of those pictures. I will just look at the appropriate pictures here. Residuals are the errors, the distances of the points from the line. What you're looking for is a picture like the one that's shown right here on the left. You're looking at residuals that are randomly scattered around zero. So you're looking for a random pattern here. The residuals should be approximately normally distributed. There aren't enough data points here to really see a bell-shaped curve in this histogram, but they're kind of spread out. They're symmetric on both sides. If you look at the second one, it's this one right here in the middle now, the residuals do not look randomly scattered around zero. They have a distinct pattern. What is it? It's a curved pattern. It's a quadratic relationship. So you would say we violated some assumption here because they don't look randomly scattered around zero. They look like they have a systematic pattern. In the third case, it's this picture on the right. Residuals, again, are not randomly scattered. They start out above zero, they go below zero, and then you have the clear identifier outlier. And in the fourth case, to get over to the right here, is what the residuals look like. They're all pretty much at the same value scattered around zero, and then one point out here that's on the zero line. So each of the residual pictures is a clue that something has gone wrong. So the idea is when you do multiple regression, we have a lot of X variables. It's not obvious what picture you can look at. Look at plot the residuals by predicted and see if it looks like random scatter. If it looks like random scatter around zero, pretty much you've met the regression assumptions. If it looks other than random, then you think you've probably violated an assumption, and again, the importance is you might be able to improve the model. So a clear kind of pattern would be if you see a cone pattern to the residuals where they're getting larger as the predicted value gets larger, or where they're getting smaller as the predicted value gets larger. Cone pattern says heteroscedasticity, maybe we should try weighted regression. If you see residuals that seem to have separate groups, look for a grouping variable. So residuals is probably the single easiest thing to look at to basically see if there's an obvious way to improve your model because one of the assumptions was violated.